Welcome, sir. Welcome, Dr. Satyajit Patel, sir.
Hello.
Yeah, welcome.
Yes.
Yeah, please, you can start the session right now, sir. Please. Shobana.
Yeah, sir. Yeah, sir. I mean. Yeah, sir. So once again, I welcome you all for the day one, session 2 of STTP program. So before starting the session, I welcome Dr. Satyajit Patel, who did his PhD from IIT Delhi in the year 2016, specialized in geotechnical engineering, and did his master's in geotechnical at assistant professor at Sardar Vallabhbhai National Institute of Technology, Surat, which is shortly called as SVNIT. His area of research includes utilization of industrial solid waste in civil engineering construction, environmental issues, soil stabilization, ground improvement, geosynthetics for road pavements. He had published more than 50 national and international journals. He had guided more than 30 ME or MTech students. And he is a life member of an Indian Geotechnical Society, New Delhi, and member of Institution of Engineers, Kolkata. He had 15 years plus experience in teaching and research. So I welcome you, sir. I just hand over the session to you to deliver your lecture on utilization of industrial slags in flexible pavement and its field evaluation through FWD.
Okay. Thank you for your introduction.
Thank you, sir. Thank you.
Okay. Screen is visible?
Yeah, sir. It's perfectly visible, sir.
Okay. Good morning to all of you. So I will talk regarding this. That is utilization of industrial slags in flexible road pavements and their field evaluation or field performance using falling wave deflectometer and bump indicator. So this is Dr. Satyajit Patel, Associate Professor at NIT Surat. That is rapid development in the field of transportation, especially in highway sector in the country, results in the scarcity of good material or conventional stone aggregates. On the other hand, the huge quantity of waste material such as the steel slag or the other slag generated from the steel plants, then copper slag, GBFS, fly ash, like this. There are so many industrial waste which is available in a large quantity in India. So utilization of this solid waste in area of road constructions after improving their strength characteristics properly can solve the following two problems with one effort. That is solid waste disposal problem, preserving the valuable land for huge dumps of waste, and second one, provision of needed construction materials, thus protecting the natural resources of stone aggregates. So these are the various materials on which I am going to discuss. That is first one, that is copper slag. So copper slag is a byproduct from the copper industry. That is when that copper ore is refined to the copper metal. So that is your, in that copper industry you will get the slag material. So whenever there is a process from the mineral ore to a metal, so always there will be some slag. Similarly, the steel slag, it is a electric arc furnace slag. So that is, and the copper slag is procured from that Hindustan Copper at Dahej in Gujarat. The steel slag is procured from that SR Steel in Hazira, Surat. So in sorry. In steel slag, there are two types of slag available in the steel plants. One is in the first step, it produces the blast furnace slag, BFS, blast furnace slag. So when the iron ore is converted into molten iron, in that step, the blast furnace slag is produced. Okay. So blast furnace slag can be in the large size like 40-50 mm or up to 80 mm also. That GBFS is that granulated blast furnace slag. So during this formation of blast furnace slag, so this is pulverized into small pieces with the help of a high pressure water jet. Due to that, the large particle of blast furnace slag during its formation pulverizes into smaller particle, which is called your granulated blast furnace slag, GBFS, which is of the sand size similar to that of sand. So the chemical composition is same, only the physical characteristics is different for the BFS and GBFS. And another one is GGBS, that is ground granulated blast furnace slag, which is used in the cement industry. So the same GBFS is being processed in the cement plant. It is grinding to a very fine powder, just like cement, and that is used in the cement. That is called your GGBS, ground granulated blast furnace slag. So all these three metals are same, only the size is different. So after this blast furnace slag is there, then molten iron is formed. So from that molten iron, when the steel is produced of different composition and different alloys are produced, so in that again they have to add some limestone, dolomite stone, all these things to which form the slag, which is called your steel slag. So from molten iron to steel production, the steel slag is formed. So this is the electric arc furnace slag. So for steel making, there are different methods. Out of that, one method is electric arc furnace. The other method is basic oxygen furnace. So this at SR Steel, they are using the method electric arc furnace. So this is the byproduct from that process, that is steel slag, or it is electric arc furnace slag. The next metal is being used here in this project is your fly ash. That is well known to all of us. Fly ash, byproduct of thermal power plant. The last one is dolime. So dolime is same as that of lime. In dolime, you can get the calcium oxide content about 40-50% only. In lime, you will get the calcium oxide percentage between 70 to 90%. So dolime, you can say it is some type of a impure quality of lime. It contains magnesium oxide. So this dolime also a byproduct from the SR steel, that whatever fine powder of dolime is being produced during the crushing of dolomite stone. So that fine powder don't get its use in the furnace. So that's why it is considered as a waste material. So instead of dolime, you can use the lime from the market, which is readily available in the market. Lime which is readily available in the market. So the pictures of various waste dumps at the site and production quantity in India. So like that GBFS at SR Steel Limited Surat, around 2.5 metric ton per year. It is produced in India. About 2.5 metric ton. That is million ton. That is million ton per year. Like your steel slag is produced around 5.5 million ton per year. Fly ash is around 230 million ton per year in India. Similarly, that copper slag, that picture of that copper slag from Birla Copper Unit Dahej, around in India 3.5 million ton per year it is produced. In this picture, that aerial extent is around 15,000 meters square. That copper slag is dumped in that Birla campus. The combination of waste materials studied here, that is for the subbase course, that copper slag with fly ash as filler, that is copper slag fly ash mix, then GBFS with fly ash as filler, GBFS and fly ash mix, then fly ash stabilized with dolime, or you can stabilize with lime. So that is one material. Then black cotton soil stabilized with dolime. So these four materials can be selected as a sub-base material. And for the bottom one, that is base, for the base course, the copper slag with fly ash filler and stabilized with dolomite. Iron steel slag with fly ash filler stabilized with dolomite. Then coarse steel slag with fly ash and dolomite. Then blast furnace slag with fly ash and dolomite. So these four material has been selected as the base material. So what is the difference between these two composition of these two materials? So if you see here, in the top, that is for sub-base, there are only two raw materials are there. One is your that slag or that's your hard material. Another one is the filler or binder. But for the base course, there are three material. That your strong that harder material like slag, then filler, fly ash, or as a polyuronic material fly ash, and binder as dolomite. So for base material, we need higher strength or higher compressive strength or higher CBR value for the road pavement, and for sub-base we need low strength. So accordingly, the material has been selected to fulfill the requirement of base as well as sub-base material. So whenever you are using some binder like lime or cement, it will increase the strength. But and also it will increase the cost. So because for base material your cost is higher, that the cost of the wet mix macadam, which is popularly used in base material, so that cost will be higher than the sub-base material. So in sub-base, poor quality of stone aggregates are being used for sub-base. So this 4 plus 4, 8 material has been investigated in the laboratory test for its feasibility to be used in sub-base and base layer of flexible pavement. So the objective, that is technical competence, whether that material are feasible and their strength fulfill the requirement as per IRC code for its use in road pavement or not, and sustainability, how the from economic point of view, from the quantity of waste material to be used based on the sustainability, how it is sustainable. Then model test, pavement model test has been carried out. Then finite element analysis using Plaxis 3D has been carried out for the road pavements. Then design to find out the equivalent thickness of this material. So how much thickness you have to take which is equivalent to a conventional stone aggregate. Okay. So see if your IRC code recommend a 250 mm of wet mix macadam for base layer, and it recommend around 330 or 350 mm of sub-base layer for say CBR equal to 3% and traffic 100 MSE. So how much thickness of your material, of your waste material, that is stabilized material, how much thickness of the waste material is equivalent to 250 mm WMM, or how much thickness of the sub-base or the sub-base material consisting of waste material is equivalent to 350 mm of GSB. So that is called equivalent thickness. So that has been derived. Then experimental work, that the basic test, that is compaction, heavy compaction test has been carried out, has been used. Then unconfined compressive strength, as this is a cemented base and cemented sub-base material, so UCS is always preferable and comfortable to compare the various mixes, various curing period and all these things. So it is easy to prepare the specimen and easy to conduct a large number of tests, that is UCS test. Then CBR has been carried out only for sub-base material, and because only for sub-base material you need the CBR value to check its feasibility. And UCS is useful for any cemented material, whether for sub-base, base or anything. Then repeated load triaxial test or cyclic triaxial test has been carried out to find out the resilient modulus and permanent deformations of the various mixes. Then after, based on this above 4 tests, the optimum mix has been selected, and on the optimum mix, the durability test has been carried out, that is wetting drying cycles. Then monotonic triaxial test to find out the cohesion and angular friction, which will be useful for the numerical analysis in Plaxis. Then X-ray diffraction and scanning electron microscope test has been carried out to study its macrostructural behavior. Then model test, Pavement model test has been carried out. Now, yes. So the different trial mixes which is adapted for sub-base material. The different trial mixes which is adapted for sub-base material. That is how much, what is the mix proportion which has been adopted for the research purpose or for the investigation. That is copper slag fly ash mix. The copper slag was replaced by a different percentage of fly ash ranging from 10 to 40% of the fly ash by weight. Then GBFS fly ash mix. GBFS, that granulated blast furnace slag, was replaced by different percentage, that is 100%, 90, 80, 70, 60% of fly ash by weight. As GBFS is a costly material that has some value-added product, GBFS has some value because it is largely being used in the cement plants, GBFS. So it will not be available to you free of cost. So GBFS has some value. That's why it has been, the effort has been made to minimize the use of GBFS. Replacement means only fly ash, then 90, 80, 70, 60% replacement of GBFS with fly ash. Then fly ash dolime mix, fly ash with different percentage of dolime, say 5, 10, 15, 20% dolime. So if you use the lime, fly ash lime mix, in case of lime, you can take 3, 6, 9, 12% of lime, because lime contains calcium oxide of around 70, 80%. In case of dolime, you need higher percentage due to its impure quality. Then black cotton soil dolime mix, that dolime percentage has been selected as 0, 3, 6, 9, 12% dolime with black cotton soil. In case of lime, you can reduce it to 2, 4, 6, 8 like that. So the different trial mixes adapted for base material, that copper slag fly ash mix, different percentage like 5, 10, 15, 20% dolime has been added with each combination of copper slag fly ash mixes which is shown earlier in the sub-base material. So for each combination of copper slag fly ash mix, the different dolime has been added. Similarly, the steel slag, that your fly ash has been added or replaced by 5, 15, 20, 25, 30 and 35% fly ash has been added to fine steel slag. And then different percentage of dolime, 5, 10, 15, 20% has been added. Similarly, for coarse, it is well known, you can easily determine in the laboratory like specific gravity, grain size. Like in your copper slag, that is passing through 4.75 mm. Copper slag is always less than 4.75. So then the coarse steel slag and blast furnace slag, a particle up to 20 mm is used in this laboratory test. Because in the laboratory, you cannot prepare the cylindrical specimen for particle size more than 20. You need minimum your diameter to particle size ratio of minimum 5. But in the field, the blast furnace slag, steel slag, you can get up to 300 mm or 500 mm diameter of very large size that need to be crushed down into smaller one. That fly ash, dolime, black cotton soil, all these things. Then the fine steel slag, fly ash, dolime mix. So these are the test results from the UCS, that is unconfined compressive strength test. So for different fly ash percentage and different dolime content, for 7 days curing, 28 days curing, the UCS value has been initially increases, then decreases. That indicate that at around 20 to 25% of fly ash content, it gives the well-graded sample. It gives the well-graded sample and giving the maximum strength. And with dolime content increases, the strength will obviously increases because dolime acts as a binder material. So with increasing lime or cement percentage or dolime percentage, the strength will increase. But after 15% dolime, so So if you compare or if you find out the requirement of IRC, so for a cemented material to be used in the base layer, IRC recommend the minimum UCS value of around 4.5 MPa. Minimum 4.5 MPa UCS value should be there in the laboratory. 4.5 to 5 MPa should be there. So based on that, the mix of around 25% fly ash, 20 or 25% fly ash with dolomite content of 15% dolomite content fulfill this IRC criteria, which indicated that this mix can be selected as the optimum mix for use in the base layer. So where at this fly ash percent of 20 to 25, the strength is maximum. So see the second figure. If you draw the particle size curve, percent passing, so for different mixes, so for this mix, around 25% of fly ash mix with steel slag, you will get the well graded mixture, SW, well graded sand. So when the material becomes well graded, its void ratio will be lowest. It is well graded, so having particle of all range, so its strength will be maximum. So you can support the argument of maximum UCS value with the help of particle size distribution curve. Geotechnical inputs for pavement design. What are the various parameters you need for a proper pavement design? First one is resilient modulus. So what is resilient modulus? The elastic modulus of a material, the simple Young's elastic modulus, which we find out from the triaxial test, the monotonic triaxial test in the laboratory. The elastic modulus of a material is the stress divided by strain for a slowly applied load, whereas resilient modulus is the stress divided by strain for rapidly applied load, such as those which actually occur in pavement. So in road pavement, there is no static load or no monotonic load. All the load from the vehicle movements will be of repeated in nature, or you can take it a cyclic load or repeated load at different frequency. So the Young's elastic modulus is the stress by strain for a monotonic load, but resilient modulus is same thing, stress by strain for repeated load. So CBR test, plate load test, UCS test, static triaxial test, all these tests determine the behavior of the pavement material under slowly applied load or monotonic load conditions only, which is unable to simulate the field conditions properly. Because in the field there is no monotonic load, in the field repeated load is there. So resilient modulus and permanent deformations are two important material properties for characterization of pavement material and design of the pavement structure. Now see here, this is the typical stress strain diagram which is obtained from the static triaxial test. So if you see here, at different cell pressure we are doing the test. So at different cell pressure, elastic modulus will be different. So at higher the cell pressure, higher will be the elastic modulus. Okay. So elastic modulus which is obtained from static triaxial, this is dependent on, this is a material property. It is a constant for a given material. So this is dependent only on the confining pressure. Okay. So for a given material and for a given confining pressure, this is a constant quantity, elastic modulus. So the resilient modulus, see the figure, you will get a very clear idea regarding the resilient modulus. So see the first figure, when we increase the load, the stress increases from 0 to maximum. Again, when you remove the load, the stress becomes 0. But there is some permanent strain has been remained in the material, permanent strain or permanent deformations. And what is resilient strain? It is a elastic strain or recoverable strain. When you remove the load, how much strain has been recovered, that is gives the resilient strain. So this divided stress, maximum stress minus minimum stress, the difference in stress divided by resilient strain will give you the resilient modulus, or slope of this dotted line. Slope of the dotted line shown in the left hand figure, that slope, that is divided stress by resilient strain, that gives the resilient modulus. So when there are number of repeated loads are there, so you will get the resilient modulus for each load cycle. You will get the resilient modulus for each load cycle. So it is defined as the ratio of cyclic axial stress to the recoverable resilient resilient strain in a repeated dynamic loading. And the permanent strain is an indicator of the rotting potential of the material. For a material, if the permanent strain is more or permanent deformation is more, so its rotting potential will be more. So there is a major chance for that material to be failed by rotting. So while it is desirable that, so both resilient modulus and elastic modulus, both are the stiffness of the material, but the elastic modulus is useful for the monotonic load, and resilient modulus you are obtaining the stiffness under repeated loading condition. Okay, under repeated loading condition, so this resilient modulus will be so much useful while designing the pavement using the mechanistic empirical pavement design or using the IIT PAVE analysis. So instead of using elastic modulus, so it is better to use the resilient modulus for the pavement design. So while it is desirable that resilient modulus and permanent strain of pavement material should be determined by conducting a repeated triaxial test, but most organizations in India do not have the necessary facilities to conduct the test. So in absence of testing facility, many state agencies and pavement designers use available empirical model to estimate or to predict the resilient modulus and permanent strain. So there are many empirical equations available to predict resilient modulus using the CBR value, which is available in the some IRC course also. Okay. So the resilient modulus of a material is a stress-dependent measure of the elastic modulus. It is function of both confining pressure and deviator stress, whereas elastic modulus is a function of confining pressure only. So in case of Young's elastic modulus, it is a function of only confining pressure. So for a given material, for a given confining pressure, it is constant, Young's elastic modulus. But resilient modulus is dependent both on sigma 3 and sigma d value. So with changing in deviator stress or load applied on the specimen, the resilient modulus is different for different deviator stress. So it is not a constant quantity for a given material and a given confining pressure. Okay, so this is a major difference between resilient modulus and elastic modulus. Now, there are so many correlations which we can, after carrying out the cyclic triaxial test, you can correlate the resilient modulus with different cell pressure and bulk stress, deviator stress, all these things that I will explain after this table. Now see here, the ASTO code, ASTO T307 code recommend the test procedure for resilient modulus test. Okay, how to obtain the resilient modulus test or how to carry out this test, that has been recommended by ASTO code. So there are two such tables. One table is for base and subbase material, other table is for subgrade material. So this table, if you see here carefully, see that sequence number 0, stress level number 0, then stress level number sequence number 1 to 50. So at the sequence number 0, that cell pressure is there 103, then contact stress, maximum stress and cyclic stress. So maximum stress minus contact stress is the cyclic stress, cyclic deviator stress. So this is the stress combinations recommended by ASTO to be applied for base and subbase material during the resilient modulus test. So at this 15 different stress combinations, you will get the resilient modulus value. So as the resilient modulus depends upon the sigma 3 and sigma d value, so that's why for different combination of sigma 3 and sigma d, we are finding out the resilient modulus value. So the first stress level, that is sequence number 0, that is called your conditioning phase to stabilize the specimen or to make it conditioning. So up to at this cell pressure and deviator stress, around 500 to 1000 loading cycle are applied in the conditioning phase. After the specimen gets stabilized means its behavior is independent of number of cycles. It attains the resilient behavior. So after this completion of this conditioning phase or sequence number 2, yes. So then we have to apply these 15 different combinations of stress levels from 1 to 15. So see the 15 different stress combinations. For the first 1 to 3, the sigma 3 is constant with different deviated stress changing from 18, 37, 55. So minimum contact stress should be there. Contact stress is 10% of the maximum axial stress. So difference between maximum stress minus contact stress give you the cyclic deviated stress. The last but one column. So at different combination of sigma 3 and sigma d. So for each stress level, we have to apply 100 number of load cycles. So to get the resilient modulus for different stress combinations. So from this test, during the conditioning phase, we will get the permanent strain behavior, and in the stress level 1 to 15, we will get the resilient modulus value for the 15 different resilient modulus value. So if you see the figure first here, see, this is the stress strain diagram obtained during the resilient modulus test. The stress strain diagram obtained during the resilient modulus test. The deviated stress versus strain. So if you see the diagram. So this type of diagram you can obtain that from the resilient modulus test. So from this diagram we can get the resilient modulus value by taking the slope of the slope of the reducing So with increasing number of cycles, the permanent strain is increasing. See here, with increasing number of cycles, the permanent strain is increasing. Say that is your after 1000 cycle, the axial strain is around how much? Around 0.04. So after 1000 cycle, you will obtain the axial strain or permanent strain as 0.04. So similarly, if you plot the permanent strain with number of cycles, so initially it increases very rapidly. After the 1000 or 2000 loading cycle, depending upon the type of material, the permanent strain gets stabilized. So this figure can be obtained in the sequence number 0 or the conditioning phase during the test. So after the permanent strain gets stabilized, up to that you have to apply the cyclic load in the conditioning phase. Then, yes, so from this test we will obtain the 15 different MR value for 15 different stress combinations. So from this 15 different MR value, now we can find out this material parameter, that is material constant, that is K1, K2, K3, like this. So if you correlate the MR value with ball stress theta, ball stress is sigma 1 plus sigma 2 plus sigma 3. Then so you have 15 different combination of MR and theta. So you will get the K1, K2 value from these correlations. Similarly, if you correlate the MR value with deviated stress, MR equal to K1 into sigma d to the power K2. So you have 15 different combination of MR and sigma d. From this, we can find out the K1, K2 value. Similarly, instead of 2 parameter, we can use the 3 parameter model. Like MR is correlated with both sigma 3 and sigma d. MR is correlated with both ball stress and sigma d. This is called 3 parameter model because there are 3 different model parameters like K1, K2, K3. So from this 15 different combinations or 15 set of MR and stress levels, we can find out this model parameters. So after getting this model parameter for a given material, so for a given material, if you know the K1, K2, K3 value, so you can predict the MR value for any stress combination. Okay, so besides the 15 stress level available, that MR value is available for that 15 stress levels. So besides that value, you can obtain the MR value for any stress level using this K1, K2, K3 value, which is a material property or constant for a given material. This K1, K2, K3. So this has been obtained for that fine steel slag flash Dole mixes. That similarly, the regional modulus can be plotted with Debater stress. Then regional modulus has been plotted with dolomite content. At higher dolomite content, you will get the higher regional modulus. Higher the binder content, higher will be its compressive strength, and higher will be its stiffness value. Similarly, regional modulus with Debater stress has been plotted here for different curing period. That is FSFD, that is fine steel slag flash dolomite mix for 0 days, 7 days, 14 days, 20 days curing period. So this MR value has also been compared with that of wet mix macadam WMM. So WMM, if you see, the bottommost line is indicate the WMM, which is very low value as compared to the cemented base material. So MR value obtained for this steel slag flash dolomite mix, even if for 0 day curing, its MR value is more than that of WMM, because WMM is an unbound material. WMM is unbound material, so in the laboratory you will get the very low strength or stiffness. So modeling of regional modulus. So for this material, waste material, so these three model has been analyzed, that which model fits the best for this given waste material. So that we can study. Model 1, 2, 3. These three has been compared. The performance of these three stress dependent model has been compared for this waste materials. So after comparison, it has been obtained that, if you see here, the first model, that is MR sigma D model, the R square value is obtained 0.972, that is coefficient of correlations, and the residual sum of square RSS value has been obtained 12,660. So which model gives you the best one? When the R square value is highest and RSS value is lowest, so that gives the best model. So in this case, the 3 parameter model gives the best result, highest R square value and lowest RSS value. So as the 3 parameter model explain or demonstrates the effect of sigma 3 and sigma D separately. Okay, but in the first model, it did not consider the effect of sigma 3. But in the 3 parameter model, it is clearly the effect of sigma 3 and sigma D has been clearly separated by the parameter K6 and K7. So from this study, it has been concluded that the 3 parameter model fits the best for predicting the regional modulus for this cemented base material. So permanent strain after 1000 cycles, the permanent strain can be obtained after that is a 10,000 loading cycle. Up to 10,000 cycle, I have applied the loading cycle to study the permanent strain behavior of different materials. So if you see here, the WMM has the highest permanent strain. So or WMM will be highest rotting potential, as the material is cemented material. So the waste material being cemented one, its rotting potential will be quite low as compared to WMM. Similarly, the empirical equations has been developed to predict the permanent strain, like epsilon P permanent strain equal to A plus B log N. N is the number of load cycles. So for this logarithmic model, the R square value has been obtained as 0.994. So for this different material of the steel slag flash dolomite 1 day, this is the X-ray diffraction peak intensity. So from the XRD test, X-ray diffraction peak intensity, I have compared the XRD peak intensity of different mixes and different curing period. That is the different minerals or that compounds, that is calcium hydroxide, calcium carbonate, alumina, silica, ettringite, which is ettringite and CaSH gel, calcium alumina silicate hydrate. So this binding gel is responsible for the strength gain or the increase in stiffness of the material. So based on this X-ray peak intensity, we can identify whether the optimum mix is giving the higher gel formation or higher strength or not, or whatever we have obtained regarding the UCS value and regional modulus value. So that can be checked or that can be verified with the help of microstructure study. Say in case of your 28-day curing period, if you compare that 75% steel slag, 25% fly ash and 15% dolomite, for that 28 days is there and 1 day is there. So if you compare this 1 day and 28 day strength, you will get that CSH gel. In 1 day strength, CSH gel at this diffraction angle is 0 and here it is 25, which has been increased to 720 and 179. That indicated that with increase in curing period, the gel formation has been increased. So that can be ascertained from the X-ray peak intensity also. All these parameters can be confirmed from the X-ray peak intensity. So this is regarding the few photographs from the scanning electron microscope. So from this also, this is the SEM figure are qualitative in nature. You cannot quantify anything here. So if you compare the 1 day figure and 28-day figure, in 1 day figure you will not get the gel formation. Only ettringite are there. In 28-day figure, you will see the binding gel, the dense binding gel is there, which bind the slag and flash particles. So the optimum mix proportions adapted for base course. So similarly for all the material, all this test has been carried out, and based on this test, the optimum mix adapted is your, that is 69.6% copper slag, 17.4% fly ash and 13% dolomite mix. So this gives the best result of the maximum value. Similarly, fine steel slag optimum mix is there, coarse steel slag, blast furnace slag optimum mix is there. So it gives the maximum usage value, maximum resilience modulus value, and also it's fulfill the strength requirement given by IRC 37 for to be used in the base layer of flexible pavement. So comparison of this optimum mixes with WMM. So if you see here the comparison of this all this material, the WMM, that is the bottommost is that for WMM, that is diameter stress to cell pressure, and the cemented that waste material has very high value of diameter stress or failure stress as compared to WMM. So it has high elastic model also. Static test elastic model in the 460, but you can get only 100 MPa only. 100 maximum 150. Model of the cemented waste material compare WMM. All the material has value modulus compared to WMM. Model parameter for the model 3, that's parameter model. The constant can be, you can find out for different like CF, copper slag, and blast slag, WM. So all this from the statistical analysis from the relative value of MR value for this comparison of for waste material. The pavement test, the from pavement model test. So the plate load test has been done on the pavement model, and the behavior or the performance load carrying capacity of this cemented material has been compared with that of WMM. So the dotted line indicates the model test result, the continuous line indicates the numerical analysis fluxes. You see here all the 4 waste material has shown the higher load carrying capacity as compared to WMM. So these are various parameters we use for this analysis. Like for the fluxes, you need the resilience modulus. So for the different material, the waste material, the resilience modulus has been used in the fluxes analysis. New positions has been taken 25. The density of each material has been taken. C and 5 value has been taken for each material. Okay. So this is the sigma T1, that is your tensile strength obtained at the bottom of the bituminous. So for that base layer thickness, same thickness, and for two different CBR values, 3%, 4%, the deformations at the top has been obtained. Delta deformation at the pavement top, then fatigue failure criteria. So if you see here, the tensile strength obtained at the bottom of bituminous layer has been observed from the Plaxis analysis, and accordingly the service life ratio has been obtained. So the service life ratio of 1.522, that indicates that if your control pavement or conventional pavement is designed for 10 years, then this CFD material will last for over 15.2 years. That means its service life is 1.5 times that of conventional material. So that service life of any material you can determine with the help of this numerical analysis. Similarly, the equivalent, so based on that that horizontal tensile strength, which is shown here in the previous table, if you can plot with the base thickness, so the top line indicates the WMM, wet mix macadam. The bottom four lines are corresponding to the cemented waste material. So you can find out the equivalent thickness. That is 250 mm of WMM is equivalent to how much? Around 100 mm of waste material. So see the thickness difference. Due to this cemented base material, as it has higher stiffness, higher strength, so around 100 mm of this cemented waste material is equivalent to 250 mm of wet mix macadam. So see the thickness difference. So there will be huge cost saving. So this is based on the fatigue criteria. So all these conclusions are there, whatever we have discussed. So similarly, these are the optimum mix which has been obtained for the subbase material. Out of this subbase layers, 4 materials, that black cotton soil plus 90% lowline mix, fly ash plus 10% lowline mix, 70% copper slag plus 30% fly ash, then 10% GBFS plus 90% fly ash. So this mixes satisfied the strength requirement or CBR requirement for a subbase material. Now, pavement performance monitoring. How we can evaluate its field performance? So there are two field equipment are available. The first one is falling weight deflectometer. So see the figure, the deflection bowl. So when you apply the load with that loading plate of diameter 30 centimeter, which is same as that of wheel diameter or tire pressure. So when you apply the load, the deformations will be there up to some distance. So if you measure these deformations at different distance, you will get this deflection bowl, and from this load deformations curve, you will be able to find out the stiffness or elastic modulus of all the 5 layers of the pavement. Based on this simple Burmeister theory, so from this instrument, the load is applied at the loading plate, and the deformations are being measured with the help of geophone at different distance. So from this we obtain the stiffness or elastic modulus, or that is the dynamic modulus, because you are applying the load, the dynamic loads are being applied or repeated loads are applied. It is not a static load. So whatever modulus you will obtain, that is the dynamic modulus, or that you can correlate to resilient modulus also in the field. So this is the equipment available, that falling weight deflectometer equipment available at our institute, SVNIT. This has been procured as a part of the DST project. Okay, and so it is supported by 2 axle, 4 wheels. The loading plate, you can see that glass box is there. Inside that, the loading plates are there of different weights. So based on the required load target load, the loading plate raised to its height, the required height automatically, and there is a free drop of this loading plate from that height to apply that much stress. And the geophones are fitted along its axis up to length of 1.8 meter. Then the second instrument is the International Roughness Index. The first instrument, falling weight deflectometer, that gives the structural performance or the how to evaluate its strength or that stiffness. Okay, that structural evaluation. This instrument, that roughness index, this gives the functional evaluation. How much, whether the road is rough or whether it is smooth. So how to measure its roughness? That is also one of the important criteria. Even if the road is of very good quality or very good stiffness is there, but the smoothness should be up to that required limit or up to the required level. So to measure this roughness index or smoothness of this road, there is a parameter in International Roughness Index (IRI) value that can be obtained. So in India, roughness is measured using fifth wheel bump integrator developed by CRRI New Delhi, and it gives the unevenness index UI value in mm per kilometer. So that is converted into International Roughness Index (IRI) equal to UI divided by 720. So that can be, roughness index can be calculated by using the bump integrator. So from this instrument, when you toward this instrument at a speed of 30 km per hour at a standard speed, so this wheel will jump over the due to this unevenness on the road surface. So during this jumps, it measures the height of humps or the unevenness during its travel, and per kilometer how much unevenness has been obtained or has been observed, that can be calculated. So this is bump integrator. From this roughness index can be calculated. So for airport runway and superhighway, the roughness index should be less than 2. That is 2 meter per kilometer or 2 mm per meter. So per kilometer stretch, the total unevenness should be less than 2 meter. Then it is called very good quality of pavement, like for airport and superhighway. So higher the roughness index, poor is the quality of pavement. Now, so as a part of the DST project, we have used this optimum mix, whatever laboratory test has been carried out, and I have explained just now. So based on that laboratory test, this mix has been selected as the optimum mix for use in the field. So instead of dough lime, here we have used the lime obtained from the market. Okay, that is copper slag, that CCF copper slag and lignite flash, then copper slag flash lime, steel slag flash lime as a base material, in sub base flash GBFS, flash lime, and copper slag flash. So three base material, three sub base material has been taken. So all these combinations, optimum combinations, satisfy the requirement of IRC 37 as a base and sub base material. So these are the constructed test sections. Okay, the slide is visible? Yes. Yes. Hello.
Yes, sir.
Okay. So this is regarding the field performance of this waste material, which is being used as a part of a state highway near Surat, Gujarat. Okay, so around 24 test sections has been formed from this 6 material. There is 3 material for base, 3 material for sub base. So 24 test section has been prepared with different material and different thickness as a part of the state highway, Olpar Sahol State Highway near Surat. So 2 stretches has been prepared. One stretch is for different base material, another stretch is for different sub base material at 2 different locations nearby each other. Okay, that 2 stretches are near to each other. So these are simple photographs that during the construction steps. That so that soil of that road is of black cotton soil. Okay, expansive soil. So and the road, the thickness has been designed. The road has been designed for CBR of 4% CBR. So the only black cotton soil has CBR of only around 1.5 or 2%. So which has been improved by addition of 50% flash, 50% native soil has been taken in the subgrade layer to obtain the designed CBR of 4%. So these are pulverizing the soil, then mixing flash plus soil with a grader blade, the grader equipment with the help of a grader machine. the soil flash has been mixed, then addition of water, then compaction. And then after this is the construction, that is your taking raw material from the stockpile, that flash, copper slag that has been mixed, like copper slag, flash lime, steel slag, flash lime. So that has been stocked in the wet mix plant area, and that has been mixed manually with the help of a JCB in the Pookland. Okay, that addition of water, that white powder is the lime. So instead of that manual mixing, we can use that concrete mixer also, or some type of other equipment can also be used to get a very good quality of homogeneous mixing. So after dry mixing, you have to add the water, then you have to mix in the wet condition also properly. After mixing, it has been loaded in the truck and transported to the road, which is around 4 kilometers away from that mixing plant. So that it is that is spreaded and that compacted to and OMC MDD has been to achieve the OMC MDD. And to study the leaching properties also, we have laid the perforated PVC HDP pipe, which is wrapped with non-woven geotextile below the waste material. So in the subbase and base layer, usually in the subbase layer, because the base layer is the cemented one, which is impervious. So in the subbase layer, when copper slag flash is there and the GBFS flash is there, which is of unbound material, so that has some permeability value. So that's where we have kept the perforated HDP pipe to get the leachate if it is produced inside the waste material. That leachate will also be tested for the leaching of heavy metals if there. This is some results of that FWD results. So from the FWD test, we will obtain directly the elastic modulus of different layers and also the peak deflection D0, which is obtained at the top of the pavement. Peak deflection D0 at the top of the pavement. So for different material, different mix, different thickness, you can obtain the stiffness value. And also the stiffness has been obtained for different load intensity, like 40 kN load, 55 kN load, 70 kN load that is applied through FWD in the field itself. So if you see here in the bottom figure, the back calculated modulus, elastic modulus of different material has been obtained like this. Flash lime has been obtained 400 MPa elastic modulus from FWD test. Then copper slag flash has been obtained 180. Flash GBFS has been obtained around 210. Then GSB is a conventional stone layer or subbase material, granular subbase. It has the elastic modulus obtained as around 105 only. So this is the result from the field test, okay, which gives the more accurate result or the actual field condition. So you can see here the D0 value approximately 57% less than that of conventional GSB. Then elastic modulus of 400 MPa, which is 4 times higher than that of GSB material. So this cemented material has very high stiffness value or very high elastic modulus as compared to conventional one. So it is giving the low deflection at the top as compared to conventional one also with cost saving. Similarly here the FWD test results, base layer with base, so this is for the base layer. The previous one is the for sub base layer. In the base layer also you can see here that CCF, that lignite flash and copper slag, CFL copper slag flash lime, steel slag flash lime. So it has elastic modulus up to 600 MPa or 580 550 MPa has been obtained for CFL, and for wet mix macadam the elastic modulus is around 110 MPa only. So this indicates that how that your cemented base sub base is very economical and very good performance, or the better performance as compared to control material. Also the cost saving will also be there, that I will discuss. So that service life ratio, if you see the service life ratio from this IRC guideline, IRC 37 guideline, that whatever equation is used for the laboratory MR value and to find out the SLR value in the laboratory. So same equation has been used to find out the service life of this waste material with compared to the control material. So whatever elastic modulus you have obtained from the FWD, so that elastic modulus can be used to analyze in the Plaxis analysis to obtain the strength, that horizontal tensile strength or vertical compressive strength. From this service life ratio has been obtained. So if you see here, service life ratio is 1 for the control material. With respect to 1, your service life has been obtained as up to maximum 1.5. So for different loading intensity for different material, the service life ratio has been obtained, and it indicates that all the waste material has service life of more than 1, or that means it has service life higher than that of control material. So this is service life ratio for surface material. Similarly, service life ratio for base material. Okay, and this service life is also compared with control material of, here it is, it's 350 WMM and 300 GSB. So even if the WMM is 350 and 300 is the GSB, even though your waste material of 150 mm is giving higher service life ratio than as compared to 250 mm WMM. So roughness index from the bomb material for the for sub base and base. This is regarding the service life. This is regarding the roughness index. So see the roughness index. So that after construction, after 2 months, the 2 months after construction, the roughness. This figure indicates the roughness index IRI value, which has been obtained in the range of around your 1600 to 1800. Okay, mm per kilometer, and the the limit is 2000 mm per kilometer for the airport runway or for the super highway. So even so in the after 2 months construction, so that value is quite low, around 1600 to 1800 mm per kilometer of all the waste materials. So this is regarding the cost saving, and the quantity of waste material has been, how much has been used. This is regarding the cost saving, like that your percentage saving, your CCF, lignite flash copper slag percentage saving is 15%, cost has been saving with compared to the total cost. So the cost saving goes maximum up to 15.7%, and the minimum is around 4% cost saving. Then yeah, so this material is for different thickness. Like for if you take copper slag flash, the TS12, test section 12, if you take 400 mm copper slag flash, in that case cost will be negative because the thickness is quite high, 400. So but in all the cases the service life is more than 1. That means the service life is higher than the control material with addition to that cost saving. So by using this waste material, you will get higher service life ratio with more cost saving. So cost saving will be around in the range of 10 to 12% of the total cost. So this cost saving will give you how much? Around, that is 10% means around 10 lakh rupees per kilometer per lane. This cost saving will be around rate per kilometer in lakhs. Okay, so that is rate per kilometer in lakh. That column is there. So you'll get around, your control material is your 77 or 78 lakh per kilometer per lane, and your waste material is around in the range of 70 lakh, 67 lakh, 72 lakh, like that. Around 8 to 10 lakh per kilometer per lane can be saved by using this cemented waste material. So along with cost saving, you are getting the higher service life ratio. Okay. So these are the various that rate per meter cube has been analyzed by taking the different waste material, the different that hauling distance, the material cost. So the cost of this waste material is also not considered as zero. It has some value, like that copper slag is 50 rupees per ton plus GST. The lignite flash is can be procured at 120 rupees plus GST, like that, plus transportation cost. So even if this material cost is there, the transportation cost is there, even though the cost saving is there and higher service level ratio is there. So this is regarding the utilization of this waste material and its field evaluation. Thank you all.
Thank you, sir.
Yes. Any questions?
So participants, do you have any question? You can just raise your question in the chat box. So I'll clarify your queries.
Yes.
Participant, do you have any questions? You can just ask to sir. Sir, I think the question is coming. The first question from Mahendran. Can you able to see, sir, in chat box?
Can you read the question?
Yes, sir, sure. So what is the optimum percentage of slag?
Optimum percentage of slag.
Slag.
Yeah. So in this case, I have used, just 1 minute, I will show. Yes. So in this case, that optimum percentage of slag is taken as 70%. It is about 70%. And the flash is around 25%, and lime is taken 5 to 6%. Yeah, testing as a machinery adapted in Surat. Yes, so there are other questions I am able to see here. That
Yes,
is,
sir.
yeah, that is that testing method and machinery adopted in Surat is approved one. Yeah, that machinery, that is not no any other that additional machinery. Whatever that you are using, you can use the different machines for mix the dry mix, add the water, mix it, then compact it. The testing method is that falling weight deflectometer or bump integrator. So bump integrator is the only instrument that can be used to measure the roughness index. And regarding falling weight deflectometer, there are few equipments available in India. So nowadays there is not mandatory at present, but NHAI and the road department, they are making more and more use of falling weight deflectometer to evaluate the field performance of the road pavements. So that falling weight deflectometer testing method is already approved by IRC. IRC 115 is there, the testing method and all these things. Then next question is that Binay Suresh, instead of pliers, can we use the sawdust and sawdust S, because it will have, yeah, so if you use sawdust S, so you can check the compressive strength of this S with the slag and lime. Okay, whether it is reactive with lime or not, how much silica percentage is there in that you can check. So the material should fulfill the strength requirement of around 5 MPa after 28 days curing as per IRC requirement. If that strength is fulfilled by any material, any cemented material, then that can be used as a base material. Okay, then any special code provision available for waste material? Yeah, that asked by that Makendran, that is IRC SP20, that IRC special publication 20, that recommend the various waste material and also recommend the required compressive strength of different material. So different type of waste material is, that is stabilized with lime and cement, that has been recommended in that code, and the strength requirement is also recommended in that code IRC SP20. Then yes, will it be more realistic if the study might have conducted at lower confinement stress level, since the subbase and subgrade depth from top will be around 1 meter? So yeah, so that confinement level is not only due to self weight. Say your subbase and subgrade is only at 0.6 or 0.7 meter depth, but the confining pressure is not only due to self weight. Confining pressure may occur due to the vertical stress also. When from the top the vertical stress is there, which also increases the confining stress. So confining pressure is not only due to self weight, but it is also due to vertical stress. Yes, I will share the PPT after removing some data which is unpublished till now. So I will share the PPT. Yes, I think I have read out all the questions as been raised by different participants.
Yes, sir. I think that's a question, it seems. Further, is there any questions, participant? No, sir. I think the question is finished, it seems.
Okay.
Yeah. Thank you, sir.
Okay.
Thank you so much, sir.
Okay.
Thank you, Dr. Satyajit Patel. This is Rajan, Dr. Rajan.
Yes, yes. Thank you.
Thanks a lot.
Yes, yes.
So wonderful presentation. Thanks a lot.
Thank you, sir.
Thanks for giving this session very neatly, nicely. Thanks, audience, for asking your clarifying your doubts, asking great questions. Now, I think Shobana will tell. It's a break for lunch.
Yes, sir.
You can join back. All of us can join back by 2 p.m. sharply. Dr. Balkumar will be addressing in the afternoon session. Thank you, sir. He's very much available here. Thank you.
Yes. Thank you, sir. Thank you, Rajan, sir. So as Rajan sir said, we just have a short lunch break. So we will be back for the session 3 of day 1. Start at 2.
Ma'am,
kindly fill the feedback. Yeah, we will be posting frequently. So kindly fill your feedback in the feedback link, which is posted in the chat box.
We will let us post the feedback for the first session also again, so that if somebody has missed, let them do it. Fine. Okay.
Yeah, sir. Okay, fine. So for the first 2 sessions, the feedback link will be posted. So you just kindly fill your feedback in the and be present for the session 3 of day 1 STTP program, which is be held at 2 p.m. By Dr. V. Balakumar, sir. So thank you, participants.